a topic that has gets a lot of attention, also a lot of questions about how feasible is it, how long can I store energy, at what temperature level can I store energy. Well, hopefully today and this afternoon you will get at least the first answers on those questions, and also insights in business cases, and also if you can apply it at your company. Well, let's start with the basic rules of the webinars. That first of all, the webinars will be recorded, and also the slides will be shared afterwards, so you don't need to take notes of all the slides. A question also is to switch off the mic and the camera if you're not the one that's presenting. And the last one is use the chat option for questions, so that we can just collect all the questions and ask the questions to the speakers after their individual presentations. Well, also already mentioned by Frank. Well, of course, with the welcome by Frank, my colleague Eva Juffermans will start with a general overview of the heat storage technology. And then we have indeed three vendors of heat storage techniques, and all of them will present their own storage technique. We'll start with Carlijn Lahey from Energy Nest. We'll continue with the thermal battery for industry. From Elena, we will present the Kyoto Heatcube technology. And last but not least, we will have Cedric Fritsch from Craftblock, and he will mention how to do the pioneering in high temperature energy storage. And just before 3, we hope to close the session and then also share the survey where you can well, give feedback on the presentation and also come up with suggestions for further webinars. Before I give the floor to my colleague, I would like to ask everybody to go to menti.com and use this Mentimeter code, so we can have 3 or 4 quick questions just to get an idea about the knowledge of high temperature heat storage that you gain, and also where you think the opportunities are for your company. So we'll just share and start the Mentimeter code. So go to menti.com and use the code as provided. 1 second. The code is given also in the slide, so it's 29286010. So go to menti.com, dial in the code, and go to the first question. The first question, the answers are coming already. What do you see as the biggest potential of high temperature thermal energy storage for a company? Is that probably the most obvious answer, lowering the energy cost? Does it help you to electrify in congestion areas? Does it help to increase the sustainability of heat? Can you use it to valorize waste heat, or is there any other potential you see that's not listed in the form? Just give it some 20 more seconds and see what the outcome is. And it's probably also good for the presenters later on to see if they can also make a connection to the answers as given now. What we clearly see here is that a lot of people think that it will really help to increase the sustainability of heat. So not that much of lowering energy cost, not that much to help electrifying congestion areas, while it might really give some opportunities there, and a bit more to valorize waste heat. Okay, let's go to the next question because we have a rather packed program. Are you looking into thermal energy storage for your company? Did you already start? Did you already have one on site, whatever size it is? Are you ready to invest? Do you start working on business cases, evaluating it, or is it not in the picture yet? Okay, that's good to see that a lot are already starting to evaluate their business cases. So then really this webinar should also help you to get some more insights. Currently not looking into it is like almost the rest of the people, and nobody has it on site. Somebody might have it on site, but probably do not see that as heat storage, and nobody is in the status yet that they are investing in it. Okay, let's go to the last question before we dive into the real presentations. There are always talks about what time frame for the storage do you want, do you need, do you store it, do you need to store heat for like months, do you need like seasonal heat storage? Does it need to be stored for weeks? Do you need to store the heat for days, for hours, or for minutes? So what time frame, time scale of heat storage are you looking for? What would really help your company? So no seasonal storage yet, no weekly storage, just between days and hours. Well, to me, that's a good insight that usually like short-term duration storage is required, so not minutes. So it's not really to stabilize the heat production and consumption, but more like to bridge hours and days gaps. Okay, so I will stop the presentation right now and give the floor to Eva to start with the introduction. Questions can be asked in the chat during the presentation and afterwards as well. So, Eva, the floor is yours.
Thank you, René. So what I would like to do today is to give you a short introduction of high temperature heat storage. And I would try to keep it short. There's a lot to tell, but there are also a lot of others with interesting things to tell. So I am a consultant at Blue Zeta. working on energy solutions for industrial parties. And for high temperature heat storage is usually, for us, high temperature means at least above 100 degrees Celsius and usually above 120 degrees. This is usually our definitions for high temperature, because for lower temperatures below 100 degrees, you are usually looking into water as a storage medium, because water is relatively cheap and very easy to deploy. However, the higher temperatures, it is not always the best solution, which I will go into in this presentation. High temperature heat storage is a growing market. However, it is certainly not a new market. It is growing because of the changing heat and power generation sources, because nowadays sustainable sources such as solar and wind require flexibility, and therefore new applications and business models are developed. However, high temperature heat storage on itself is not that new. In this slide you can see 4 examples. One of them at the top left is a regenerator. This specific model is also known as a copper stove and is used often in steel and glass manufacturing plants. This particular one is located in Duisburg, Germany. And it has been used in the very high temperature industries, like I said, glass and steel, because the heat that is necessary, flue gases, to melt the glass and steel are at such high temperatures that normal heat exchangers are not able to withstand the heat, and therefore they use an intermittent heat source and sink in the form of ceramics, and they interchange, they switch around the whole process. So at one point they will heat up the ceramic storage medium using the excess flue gases, and at the same time use another heat medium, ceramics, which was heated up before with the excess flue gases to heat up the ingoing flue gases. And this process is changed in direction every few hours. So this is already an hourly energy storage at high temperature, which is deployed often in those sectors. On the top right, you can see a tank water thermal energy storage. This one is located near Amsterdam. It is owned by Vattenfall, and it uses water up to 125 degrees, so under pressure, to supply heat for a district heating network. And then at the bottom of these slides, you can see 2 different types of high temperature heat storage systems used for concentrated solar power. They are both located in Spain. And in the bottom left, you can see a tank with the medium is a molten salt, which can go up to much higher temperatures, about 450, 500 degrees Celsius. And at the bottom right, you can see a steam accumulator, which stores water under very high pressures, making it liquid. And by changing the pressure in the tank, you can accommodate the amount of steam going in and out required for the process for which this thing was meant. So there are already a lot of examples that are already common in industry. However, there are a lot more business cases emerging right now. So in this overview, I'd like to first zoom out a little bit to just in general energy storage technologies. On the vertical axis, you can see the discharge duration, so how long usually the duration of storage is. And on the horizontal axis, you can see the power rating. And there are a lot of different type of energy storage technologies. you can see, you should, by the way, these lines, so the dotted lines are not very strong borders. They should more, you should see them as a blurred line more. And they can extend a little bit towards left or right, up or down. However, this is the general area of application of these technologies. And in between brackets, you can see their market value. So what you can see here is that in dark blue, electrochemical and chemical on top in lighter green are very large markets. They have been deployed for many years. Of course, electrochemical, you all know, in electrical batteries. And chemical is a very vast market because it includes the manufacturing of, for example, e-fuels such as e-kerosene, methane, diesel gasoline, but also chemicals such as naphtha, methanol, and waxes, which is also a form of energy storage. Then, of course, depending on how long you want to store it, so seconds towards even seasonal storage, you can see that the type of storage will already be limited by the duration that you prefer. So, for example, if you want a storage duration of seconds to minutes, then flywheels or supercapacitors are your thing. However, if you want it to go more towards days, you have to store it in a vastly different methodology. So for now, we will be focusing on thermal energy storage. And in thermal energy storage, there are generally three types. The first one is sensible heat, which is, it's basically described in the name. You can sense it, you can feel it. And it is a very common example is your gas boiler or electric boiler if you have one. However, the point of sensible heat is that you store heat in a material without the material going through any phase, through any change, so either phase change or a full transformation towards another molecule. It's basically just storing heat in a material through which the material heats up. Then the second type of thermal energy storage is called latent, which is when the material does go into a phase change, for example, from water to ice. That is a latent heat storage. And the third one is thermochemical, which is when a chemical reaction takes place, which is usually reversible. So common media for these types of energy storage for sensible are, for example, water, but also thermal oils, salts, and stone and ceramics. And for latent heat, common materials include salts, silicons, and paraffins. And then thermochemical is often media which can perform redox reactions, such as zeolite or salts. And of these different types, you can see them as in this diagram as different colors. So sensible is blue, latent red, thermochemical orange. And they often already define in part which type of storage we're looking for. So in high temperature, then it's usually, well, in this case, you can see it above the line of 100 degrees, so medium or high, and often used is solids, of course, or molten salts, but also composite phase change materials, which is what CPMC stands for, or chemical looping, such as redox reactions. And those are usually the types of, those are the types that we are looking into right now. So what is often used? Well, like I said, there are different types of high temperature heat storage technologies which are already mature and commonly used. And those are often water tank thermal energy storage, so TTES, or molten salts, which is often used in combination with concentrated solar power. However, what we see lately in the last few years is a strong emerging of solid state and molten salts in sensible heat storage. And as you will hear later today in this webinar, there are a lot of parties who have been developing beautiful technologies in this area and are already commercially available and even have a track record of some sorts. So, however, the latent and thermochemical technologies, as far as we can tell, they are often still in prototype, perhaps demonstration phase, but are less mature. Now, what kind of business cases can you think of? Well, the first that people usually think of is additional capacity, so waste heat valorization. Although I saw in the questionnaire before that actually the second of this list is also thought of frequently, which is really nice. But so there, in our view, there are three different types. So first one is indeed additional capacity, so waste heat valorization, but also it's an increase in available power and capacity, which is not always available on site, which could be either through net congestion or also because you do not want to pay more CO2 credits. And another case of additional capacity, you can use it as backup capacity, so emergency capacity. Then another type of business case is surplus energy utilization, which, oh, actually, this is where the waste heat valorization comes in. However, another very important emerging application under this is the surplus in energy supply. So this might be either because you have a maximum contract capacity, which you cannot go over, of course. However, you often are not all the time at your maximum capacity. So there are points in time where you could draw more capacity. However, this does not match the processes that you require energy for, which, of course, through thermal energy storage, you can valorize this extra capacity. And then the last, which is, I think, might be overlooked at sometimes, is market balancing. And you can see market balancing, you can see this into two sub-points. One is, of course, market balancing on a more view where you play into the amount of electricity available at that day. So at sunny days, you can trade because electricity prices are lower. You can do this through day ahead trading, intraday trading, or simply by going into power purchase agreements, which can give you a much more value for money for your energy required. However, another important part is the frequency reserve. And if you have a large capacity at hand, which you can scale up or scale down very quickly, so we're talking about seconds actually here, seconds to minutes, then you can also apply for the frequency reserve. Well, I believe that the suppliers will tell you also more about this. So, and there are, like, every business case that we've seen until now is very specific. So I rather than giving you an example of a business case, I would rather turn it around and look at the investment scope that you can have for different types of energy storage business cases. So on the left of the table, you can see different types of energy storage duration. And in the first column, second column, the amount of cycles per year that are roughly associated with the term are depicted. Then with a 5 megawatt hours thermal energy storage, you will save in a year or in 5 years, you will save the amount of energy in the third column. And with a electricity price of 40 euros per megawatt hour, you will have an energy price savings of the amount in the fourth column. If you count this in 5-year investment times, if you want to have a payback time of 5 years, that means that for seasonal storage, you have a very low price per megawatt hour for which you can buy or invest in an energy storage system, around 200 euros per megawatt hour. If you increase the amount of cycles that it will have each year, then you will very strongly increase and very quickly increase the scope of investment. So what I want to tell you here is the more cycles the battery makes, the more profitable it will often become. Then
you have just 2 minutes left, Eva.
That is perfect. Thank you. So this is what I really would like to give to you and the suppliers in the next few presentations will probably give you much nicer examples of specific cases. But there are a lot of suppliers, either who have already been in the field for years or who have emerged in the last few years with beautiful examples of very profitable thermal energy storage cases as well. So here you can see an overview of suppliers that I have, we have been in touch with over the last few years. And some of them, there are quite a few of them are Dutch, but there are also larger companies who have been in the field for a long time and from European sources or even American. So there are a lot of suppliers that can already fix these solutions for you. And I'm very curious to what they will tell in the next few presentations. If there are any questions, I'm not sure if there is any room left, but this is in any case what I would like to have told you for the introduction.
I would say if there's time for one question, so if somebody has a question, please feel free to ask the question or put them in the chat so we can answer them later on as well. If not, then I have a short question from my side. I see a lot in phase change material, a lot of research going on already for decades. If I see your list of the majority of heat storage techniques, they're not really high in the list. Do you expect that to change in the near future? And also, why is that they are not really market ready yet? Because everybody wants to have a storage material that charges and discharges at almost the same temperature. Can you just give a very short insight into that?
That is a very nice question. If I go to the suppliers slide, well, yes, so I've seen that too, of course, that there has been a lot of research into this area. I do know that, for example, PlusSat it does do this, but for very specific applications, and it is usually for applications where there is no area available, no physical area available to put large systems. For example, they use it for cooling transportation. However, it is often because the materials are harder to process. Even if they have managed to keep the phase change stable and to be able to have all the other specific technology requirements developed, even then the price remains higher, which is why usually solid state and sensible heat storage is more profitable. Oh, René, I think you're muted.
Yeah, thank you for sharing the insight on PCM, why it's not there and why it's probably not being part of the storage in the near future. So it really has its specific use. Thank you for sharing the information. I think we'll just switch on to the next speaker of today, which is Carlijn Lahaye. So Carlijn, the floor is yours.
Thank you. Let me share my screen. Yes, that worked. Good. Good morning, everyone. Good afternoon. Sorry, my name is Carlijn Lahaye. I'm the Managing Director of Energy for the Netherlands, and one of the 3 suppliers that will share more about their technology today. On the picture, you see one of our references is at Yara in Norway. It's been in operation since January 2023. So you saw Eva's overview with where solid state is, and that overview was from 2020. And all of us, all 3 here today, have developed projects after that date. So happy to share that. We have currently 3 projects. So Yara, I just shared. We're building at ENI, which is at the refinery in Sicily. And then there's a project at Avery Dennison in Belgium in Turnhout. Avery Dennison is an adhesives manufacturer. All 3 of us, I think, are solid state batteries. We as well. Our storage material is a type of concrete. This is developed with Heidelberg Materials. And one of our main shareholders is Infra Capital, which is an infrastructure investor. They also own railroad and trains and stuff. So they really invest in us for the long term, which is very helpful and very pleasant to have such a good investor. Well, I think Eva also mentioned this briefly, and you also mentioned it in the Mentimeter answers. Why do we need thermal storage? Well, we need to decarbonize our energy system. And if we decarbonize our energy system, direct electrification is a good route. But that means you have intermittent renewables, solar and wind, that are only there when the weather allows it. But your process is 24/7, needs to be reliable, needs to be cost competitive, and that doesn't always match. So you need buffers. And these can be electrochemical batteries, these can be molecules, or this can be in the form of thermal storage if you are, for example, in the MVO industry and you need a lot of heat. So in that case, I think thermal storage is one of the best ways to go to bridge intermittent sources and your continuous, or at least with your demand with a different profile. So flexibility, in my opinion, is key. And how can you then apply thermal storage? For the Netherlands, I would say electrification. This is also, I think, what this webinar is about. So you want to decarbonize your heat supply with electricity, and you want to benefit from times that electricity is cheap. You want to maybe support the grid, right? Or provide ancillary services to TenneT. In the case of thermal batteries, automatic frequency response rate is the market you would be, or the frequency service you would provide. And then also more and more grid operators in the Netherlands come up with flexible contracts, which means you get a reduction on your grid costs if you are flexible. And some grid operators like Steden have even announced that they will enforce their customers to be flexible because they just don't have enough flexible demand in their grid, and it makes the grid, the grid becomes too unstable. So we need to become more flexible. Our typical temperature range is 130 to 400 degrees Celsius. So this is perfect for food and beverages like yourself, chemical sector, part of manufacturing, pulp and paper, part of refinery. So any process heat between 130 and 400 degrees Celsius. Other applications, waste heat recovery, there was some interest in that as well. we can have, I'll mention it later, or I'll get back to that later as well. With as heat transfer fluid, we can work with direct steam or with thermal oil. Waste heat recovery, if you have high temperature waste heat, it's a solution, but we cannot do anything with like 120 degrees heat, unfortunately. So it needs to be higher temperature. Steam grid balancing, that's the application at Yara. So they have exothermic batch processes, generates a lot of heat. Our battery cycles a few times an hour to recover that heat and to make it available at another steam grid. Yara really considers this as a piece of pipe, which is to me a compliment, as a piece of pipe in which they can store energy. So we're directly integrated in their heat grid. And concentrated solar is the application at ENI and Avery Dennison. We're integrated in the thermal oil loop of the concentrated solar plant. So these parabolic mirrors, you have this loop, and then there's a heat exchanger with the customer. And that's typically, well, we have a plant, of course, in Belgium, but I would say this is more for Southern Europe. So for Spain, Portugal, Italy, Greece, because the higher the solar intensity, solar radiation, the better. What does our technology look like? This is one module, as we call it. So this is kind of the core of our technology. It's the size of a 20-foot container, and it consists of steel and concrete. So this concrete is specifically developed with Heidelberg materials, that it can store a lot of heat, that it can transfer heat well, and that it has the same expansion coefficient as steel because you don't want it to crack. So it's solid. There's no moving parts, which is why it has a very long lifetime and doesn't need any maintenance. Of course, it needs inspection. So all the headers are on one side. The balance of plant has, of course, moving parts. The balance of plant has pipes, valves. So that is something that needs maintenance, but nothing a plant is not used to. The question you often get asked is, what is the capacity? Well, that depends with thermal storage on temperature in, temperature out. So the larger the difference between temperature in and temperature out, the more heat you can store in the exact same module. So this module can store up to 2.2 megawatt hours thermal. That's with the highest temperature difference. But the lower the difference, the less you can store in this exact same module. So it's really, as Eva also said, business cases are very customer specific. Not only the cycling that Eva mentioned, but also the temperature difference is very determines the business case. Another question you always get asked is, what's the efficiency? Over a 24-hour period, you lose about 2% over the battery. And then, of course, if you have a larger chain, so maybe an e-heater, maybe even a PV field, etc., then the round-trip efficiency, again, is customer specific. The longer the pipes, the more you lose. But just the battery pack is 2% over a 24-hour period. And for the Dutch case, in which the reference is natural gas, the carbon payback time, so not the euro payback time, but the carbon payback time is about 4 months, meaning the carbon emissions that go with the whole life cycle of the battery. So producing the concrete and steel and operating the plant is about, or the battery is about 4 months. And the technology is scalable. So you can stack these modules up to 5 on top and then as many next to each other as you would like. I also already mentioned the heat transfer fluid. So you see the modules build up out of carbon pipes filled with concrete, and these little holes are the piping for the heat transfer fluid. And this can be either thermal oil or steam, depending on the customer needs. And if you then stack the battery, the heat transfer fluid flows from top to bottom to heat it up, and from bottom to top to cool down or to release the heat to the customer. Well, this is the installation at Yara. So you can see there's 4 modules stacked on top of each other. The heat transfer pipes are, of course, interconnected. You insulate it, and then you put the cladding, and this is the balance of plant with the pressure vessel, because here the heat transfer fluid is steam. So you need a pressure vessel. This is a rendering of a power-to-heat system with thermal oil. So how does that work? You have electrons from the grid, hopefully generated by wind power, or you have maybe your own PV or wind on site. You convert the electrons into heat via the electric heater. And when, for example, it's very sunny and electricity prices are low, the electric heater converts the electrons into heat. It can supply directly to the customer and can charge the battery. The thermal oil can then in the heat exchanger be converted to another, like exchange the heat with another type of oil, maybe with air, maybe it's a steam generator to convert it into steam, depending on the customer needs. And the operational modes are very flexible. So you can, if it's very sunny, for example, you can both charge the battery and supply directly, or just supply directly, or just charge the battery. And the opposite is true as well. If electricity is very expensive, you can just supply from the battery. Or if it's a bit expensive, but you need to, for example, you have, for example, peak demand once in a while, and you don't want to have a very large connection, or you want to reduce your electricity costs from the grid operator for your peak, do peak shaving, you can also supply both directly from the grid and the thermal battery in combination. So in the rendering, you would have the modules, you would have the electric heater to convert the electrons into heat, then the heat exchanger to convert the hot thermal oil in whatever heat you need. Is it air, steam, or another type of thermal oil? Of course, the balance of plant to with the pumps and the piping, the superstructure, and then this client interface to control and monitor the thermal battery. This is the basis of the business case. You want to, first of all, well, you want to decarbonize, right? That's the basis, but then you want to exploit times of low energy prices. So this is in this graph. If the prices are low, you want to charge your battery. And if the prices are high, you want to discharge the battery, which is shown here as well. So when do you want to charge? You want to charge when electricity prices are low. So typically in a 24-hour period, there are some times that electricity prices are low, and there are some times that electricity prices are typically high. So in the morning, it's typically high. On summer days, in the afternoon, it's cheap. In the evening, it's higher again. And then during the night, it's super expensive. So then you would have 2 periods during a 24-hour day that you can charge, of course, depending on the season. Then you want to probably charge if the grid frequency is high and tenant needs support. You can actually you get money for being available, and you get money for being called upon. So if then tenant steers you up to decrease the frequency, you get this also adds to your business case. And then you can have choose to have a flexible contract with your grid operator because you have a buffer, you have a thermal battery, so you can be disconnected for like not have electricity supply for a bit to a certain extent, because you can supply your processes from the thermal battery. And this is an example of what we do if we do a feasibility study. So if you think thermal storage may be a solution for you, we, and I'm sure Kyoto and Kraftlok as well, are very happy to talk to you. And what we typically do is a feasibility study. So we make an analysis of your hourly thermal demand. So this is, for example, for a food company. We do a sensitivity analysis to determine what would be the best configuration for you. So you may have a minimum decarbonization rate that you want. You may just want to have the most cost-effective solution. Maybe you have waste heat that you want to integrate, or PV that you want to integrate, excess PV, for example. So excess solar power that you also want to convert into heat. So all these elements we can take into account. I have 2 minutes, or?
Yeah,
I
3-4 minutes.
I see you pop up. Okay,
That's right.
I'll wrap up. So we do a sensitivity analysis, and with you determine the best sizing and show you what your decarbonization rate would be. So this specific customer will decarbonize 96% and have 4% left to cover with natural gas. And based on that, we can price and size your system. So briefly go over. So this is the Yara example that I've mentioned. And just what I want to stress here is thermal storage can cycle a lot. So this one is designed to cycle 462,000 times. And that's a big difference with electrochemical batteries. So thermal batteries, you should use them a lot. This brings your capex per megawatt hour down. This is the example of Ivar Dennison. So it's a 2x3 configuration. Let's use the time for something else. This is what it looks like today. So these are the parabolic mirrors. This is our battery system. This is the side. And then what I want to stress is, I think thermal storage has a lot of added value for the MVO sector. To me, flexibility is worth a lot. And this could be in the form of thermal storage, especially for your sector. Dutch cases are, of course, typically hybrid, so you will probably already have natural gas, and you consider combining it with an e-boiler or e-heater, and then maybe also thermal storage. So this is a typical configuration for Dutch customers. If you're interested, we can easily provide you with a pre-feasibility study. This is free of charge, and it's fairly quick. So just reach out and we can look into your case. And I got the question, what improves the business case? Well, if you provide ancillary services, it helps a lot. The more variable your demand is, the better the case will be. And if you have on-site renewables, the case also gets better. Yeah, happy to answer any questions. I saw one in the chat, haven't read it. Yeah, other questions are welcome as well. René, do you want me to start with the one in the
Yeah, thank you, Carlijn, for the clear presentation. I see already one question in the chat. I will just read it. Carlijn, what was the financial payback time in the Yara example? Can you please share?
There was very brief because it was subsidized both on our end and the Yara end, and it cycles a few times an hour. So it will have been like within months or even shorter because they really use it a lot, and then the capex is just nothing in the end, right? Like it's free steam. They used to dump it in the fjord. In that situation, you wouldn't dump this high quality steam in the fjord, but in Norway, energy prices were a lot lower. Nowadays, they also increased. So yeah, that was very brief and not representative for a Dutch case, I would say.
Okay, thank you for that. Yeah, so the message is indeed try to have a high cycle number, so a very short storage time, so you can use your battery quite often. So indeed, the price per megawatt hour really reduces. So rather than seasonal storage, use it. I think that's always.
Yeah, I would say industrial storage, you need to cycle on average at least once every 24 hours. And not from a technical perspective. I mean, of course, you can store it for years, but from a business case perspective, indeed, the more cycles, the better.
Well, thank you very much. And I think it's indeed required if you go into a more CO2 neutral society. We really need storage capacity. So from a nice to have, it will be a need to have in the future. Thank you very much, Carlijn. We'll just switch to another speaker, and in this case, we'll just switch to Elena, who will tell us about the Kyoto thermal battery. The floor is yours.
Thank you very much. Very nice. It's a big pleasure to present today here for you. And I see that we are like limited a bit in time, and I want to tell you as much as possible. So just a few words about myself. I'm a business support associate, and I represent the Kyoto's commercial department. And I will go straight forward to our technology and what is it about. So as of now, there was a big challenge, and all industries, and not all industries, the whole world, we need to decarbonize because we are not on track to limit the rise of global temperatures. And it's quite clear the solution is just the electrification and transition to the renewables. But then new challenges are coming because using renewables, it's always to be dependent on the price volatilities. And here where our company is coming with our solution, like a missing puzzle. So our technology called HeatCube. It's a flexible, modular, and customizable thermal energy storage that is capable to deliver on-demand heat. So just easy speaking, it's the electrical boiler, but with the battery. So the idea is to charge the battery whenever electricity prices are low during the night. Then in the afternoon, we have the off-peak hours. If HeatCube is connected to the off-grid solution, then of course, when it's sunny or, for example, windy, if it's a wind farm. And then HeatCube can deliver heat in form of steam whenever it's needed for the production process. So what of HeatCube consists? It has three main parts, and the first part is the charging part that consists of the resistive heaters that should be connected to any source of electricity. Then we have the biggest part of the HeatCube, that is the storage, and it consists of the tanks that are filled with molten salt. Molten salt is the heart of the system. It's our storage medium, and this storage medium is proven and already in use for many years, basically in the CSP plants, because CSP plants, they are using molten salt storage to produce electricity 24/7, even when sun is not shining. And then the third part of the HeatCube is the discharging part that consists of the steam generator. And the steam generator should be connected to the feed water, samely as your current boiler. So I have a video to show you how the system runs, how it works inside. And before I start the video, just want to explain that molten salt, it behaves just like a water, so it's like liquid. And on this video, the blue one is the cold and discharged molten salt, and the red one is hot and charged. So whenever we need to charge the HeatCube, cold molten salt goes through the electric heater and then comes back to the system as hot and charged, and here red on the video. And whenever we need steam for the production process, it's the opposite situation. Hot and charged molten salt goes to the steam generator where the heat exchanging is happening, and this is how we are getting steam. Due to the fact that charging and discharging parts are separate from each other, our HeatCube can charge and discharge simultaneously. And what does it mean for us? It means that we can get steam 24/7 if needed without any interruptions, and the charging of the HeatCube will be activated only during the hours that we will choose for charging. So during the off-peak hours, or at night, and then in the afternoon, or then any other hours, depending on the case, depending on the application. Due to the also our HeatCube is a flexible system, and it has a very fast ramp time that is about 90 seconds, and that is why HeatCube can be activated as an asset to balance the grid. So mainly when you are using HeatCube, you buy electricity on the spot market, in a day-ahead market. Then you can optimize it in the intraday market, and then you can get additional revenues by activating it as an asset to balance the grid. So to say, usually we are taking 8 or maybe 10 the cheapest hours during the day to charge the HeatCube, and then we can decrease expenses of these 8 cheapest hours by about 25%, thanks to the additional revenues that we are getting from balancing the grid. In addition to that, our Heatcube is the world's first IE-powered thermal energy storage. Here on the right-hand side, you can see two pictures. One picture is the real Heatcube that we have in Denmark in operation as of now. And a bit lower is the digital twin that was created to the Heatcube. On this digital twin, we have about 600, I think, sensors. And all this is connected to the app that was created for this digital twin. So our Heatcube in Denmark, thanks to digital twin, can be operated remotely. We don't need people on site all the time. The system shows the performance analysis, and the system sends signals if there is needed some predictive maintenance. Thanks to that, we can guarantee quite high round-trip efficiency. The round-trip efficiency, I mean from power to heat, at minimum level of 93%. And this is how we are minimizing the downtime of the Heatcube to maintain it and to avoid corrective maintenance. So I'm happy to present you the video of the Heatcube. On this video is the Heatcube of 56 megawatt hour of storage capacity. And this is exactly the Heatcube, the prototype of the Heatcube that we are installing in our second project now in Hungary. So here you can see that this Heatcube has 8 tanks. 7 of these tanks are filled with molten salt, and we always need 1 additional tank for the circulation process. And then to have this opportunity to charge and discharge simultaneously. Now video will walk us through the Heatcube a bit closer. And here is on the left-hand side is the heater to charge the Heatcube. So the molten salt goes through it. And then on the right-hand side is the steam generator to discharge the Heatcube. So our Heatcube is sustainable and environmentally friendly system. There is no ethics certification needed. Our molten salt is non-toxic. There is no pressure in tanks, and it's not flammable. And mainly it consists of steel, salt, and steam. And I want to touch a little bit the main features of the Heatcube. As I mentioned already, our Heatcube has customizable and modular design, and depending on your needs and depending on the site steam demands, the configuration of the Heatcube can be different. So we have 3 main parts, as you remember: the charging, the storage, and discharging part. So the storage part, the biggest one, can have any storage capacity between 16 up to 120 megawatt hour. So 1 tank has the capacity of 8 megawatt hours. So by adding each tank, we are increasing the storage by 8 megawatt hour. If you talk about the temperatures inside the system, our molten salt, when it's charged and hot, it has the temperature of 415 degrees. And after the discharging of our molten salt has the temperature of 190 degrees. Then the charging capacity of the Heatcube also can be different. So the heater to charge the molten salt, to heat up the molten salt, can have different capacities, again, depending on the case, depending on the needs and demands of the site. And it can be 10, 20, or 30 megawatt. And the discharge effect also could be different, up to 20 megawatt. And our Heatcube discharges in form of steam with any temperatures up to 400 degrees and any pressure from 3 to 40 bar A. And then we also, of course, can cover such needs as different grades of steam, and also if it's saturated or superheated steam. Then if to talk about the footprint of the heat cube, it really depends on the storage capacity, and it calculates from 100 to 250 kilowatt hour per square meter. But just to give you like an understanding and feeling, so the heat cube that was on the video with the 56 megawatt hour of storage capacity has the footprint of about 400 square meters. So our company, same as a heat cube, flexible system, and we are also quite flexible, and we are offering different business models to for cooperation. So just the simple one is as we call heat as a product. When the company orders the heat cube, then we are taking the project. We are doing the whole installation, and we are doing the commissioning on site. We will make the training of the people on site how to operate the heat cube, and then we will hand over the system to the customer. This is that traditional product sale. And at the same time, we are offering heat as a service, and I want to tell you a little bit more about this. So heat as a service model is when we will own the heat cube, we will operate it, and this is how then we are taking the whole we are taking all market risks on us, and between us and the customer is just the heat purchase agreement, and the customer is only paying for the supplied steam. So in our heat as a service, we guarantee savings compare to the natural gas-based heat, and also company then will have an opportunity to eliminate CO2 emissions caused by process heat, and then it can get additional revenues by trading the CO2 quotes. And here I'm thrilled to show you our projects. The project number 1 is the commercial pilot that is in Denmark. So this installation is for the district heating company in Denmark, in northern Denmark, in Aalborg, and the purpose of it was to decarbonize and to replace the coal, because previously this district heating plant was operating fully on coal. And this project is already in operation more than a year. It was started in August 2023, and the configuration of the heat cube there is 5 megawatt of charge capacity, 18 megawatt hour of storage capacity, and discharge capacity of 4 megawatt. So this heat cube delivers to the plant needed steam according to their requirements of 16 bar, and the temperature is 201 degrees. This heat cube, as I already showed a bit on previous slides, has the digital twin. So this heat cube is AI powered, and it operated remotely through the app. This heat cube has passed the power test that was done by local DSO, and this heat cube was activated as a asset to balance the grid. So this heat cube balanced the Danish grid. And our second heat cube is in Hungary. This heat cube is under construction as of now, and preliminary we are going to finish the construction end of this year, and start in the beginning of next year we will start commissioning of this heat cube. So this heat cube is for Coal Ingredients. It's the corn processing company, so they are producing from corn sugar, alcohol, and some animal feed. The purpose of it is again decarbonization and replacing the gas, because they are, as of now, they are producing heat with the gas boiler. This heat cube is much more bigger than the first one, with the charge capacity of 10 megawatt, storage capacity of 56 megawatt hour, and discharge capacity of 7 megawatt. And the steam that require the customer is 13 bar at 250 degrees. It's connected to the grid. It also will be activated as an asset to balance the grid. And estimated annual steam demand, delivery of this heat cube will be about 30 gigawatt hour. And this is calculating with the average of charging it during the off-peak hours when the electricity prices are low. Because as longer you charge the heat cube, as much it can deliver the steam. But we are, of course, taking only the cheap hours, and then if to charge the heat cube with the cheap hours, the performance of it will be about 30 gigawatt hour per year.
2 minutes left for you, Elena.
I think I have finished, and I would be happy to utilize these minutes maybe for the questions. I think the only point that I wanted to show also the example, because I have mentioned that we have heat as a product and heat as a service. And for example, our first installation in Denmark, it's heat as a product. So our customer is fully taking care about the installation, so they operated themselves. We have already handed over it. And so they operated it fully by itself. In this project in Hungary, we have heat as a service business model, where we have the heat purchase agreement with the customer, and customer will only pay for the supplied heat, while we will fully operate it. So we will trade the electricity on the spot market, and we will activate it as an asset in balance to balance the grid, and we will make all the maintenance and so on.
Okay, thank you very much, Elena. I think there's a lot more to tell. There's one question in the chat, and I know that from experience there's a lot of concern about using molten salt because it's rather corrosive. What materials do you use in the equipment?
Our materials is the steel, salt, that's it.
No exotic materials like...
No. It's, nothing exotic. Everything that is available on the market, so it's the steel. And this is why we are not going upper than 415 degrees to avoid corrosion, because, for example, in CSP plants, they have the temperature of molten salt of 425 degrees, and then they use special materials. But to utilize special materials, it will increase the price of the product, of course.
Okay, that's good to know, and I know that from experience that molten salt at high temperature indeed can cause a lot of problems. So you sort of prevent that by operating below 400 degrees or around 400 degrees.
Yeah.
Thank you very much once more. The last speaker in this webinar is Cedric Fritsch from Craftblock. He would tell something about pioneering a high temperature energy storing solution. And the floor is yours. And we try to finish off by 3. I know it's a short time, but good luck with your presentation.
Thank you, and welcome everybody from my side as well. I'm Cedric. I'm the communication manager of Craftblock, and you are very lucky because our head of business development couldn't be here, so I'm responsible for communicating our solutions. He's there for selling them, so it's a bit more comfortable with me, I think. What we do at Craftblock is basically what the other 2 presenters wonderfully showed you already. And we started with this journey in 2014 when we developed a specific storage material that can handle high temperatures. By 2019, we had our full-scale pilot, first recapturing waste heat and using it to save gas. This was a bit boring for us, so we said, all right, we make it mobile to fully flexibilize energy. And a year later, we did that with the first pilot. And nowadays, we are in the making of finishing a 20 megawatt hour storage at the Indian steel plant. And also, some of you may be familiar with it. Soon, the Eneco storage at the PepsiCo facility in Broek op Langendijk will be finished, which is 20 megawatt hours under execution now, but all in all, 150 megawatt hours planned. And this is really our maturity timeline. So we are in the commercial phase already and looking into each and every sector. Here you can see some of our customers and partners, some names you will know. Otto Juncker, for example, is a power-to-heat element provider, and this also already tells you that our power-to-heat elements are standard equipment that is outside the storage, so we combine the storage material and equipment very smartly to form a new system, which is modularized. And this system basically is a platform connecting renewable sources with applications to decarbonize process heat. And we can take as a source basically everything that generates high temperature heat, and with high temperature we mean 300 degrees upwards. This is where we start, so we are focusing on the new generation of CSP. We are focusing on renewable electricity that is converted into heat, and we are focusing on high valuable waste heat over 300 degrees C. But we use the same storage for each and every source. And our storage is air-driven, meaning some sort of gas is coming into the storage, and outside of the storage discharging. We are very flexible with heat transfer, a steam generator, or even hot air applications with high temperatures. How does it work? You basically saw it already, but what we have in the storage is a packed bed, as it is called. So inside is a material that is maybe fist big and round. We also can do different forms, but this is the most used at the moment. It is inside a well-insulated storage container, and from one side, hot air or gas is blown in to the storage, and the material heats up. As you heard already about sensible heat material today, this is it. Basically, the heat is sensible, and in this case, you shouldn't touch it as we go up to 1300 degrees C here. When it is stored, almost the whole storage has full heated material inside. You see on this picture it is not 100% heated. This is because at some point the excess temperature would be too high, and we want to avoid, of course, energy loss. So you can imagine it's like 90-95% charged, if you want to tell you. We can store it between hours and up to 2 weeks, but as you saw earlier in the business cases, 2 weeks usually isn't a good business case. So this is for extreme safety measures, for example.
And now it seems like we lost Cedric for a while. Let's see if we can get him back in the call. Everybody else experiencing the same problems?
Yes.
Okay. Let's see if we can invite him again. Because there was a lot more to tell about GraphBlock. Frank, can you probably remove him from the meeting and invite him again?
I will try.
In the meantime, while trying to do so, I did share already the survey for this webinar. So we can, if you have the time available, please fill in the survey so we know the feedback from you as a participant and also know what was relevant to you, where we can improve the webinars. So in the meantime, especially when the presenter is not available, please fill in the survey already. Just trying it for a minute. If that doesn't work, we will just share his presentation afterwards. We at least know what.
I think he's coming back.
So sorry about that. We have a bit of an internet issue, a well-known German problem. As you might know, I'm on with my hotspot right now. I hope this works, and I hope you can see stuff. Terribly sorry for that.
No problem. Glad you are back. So yeah, try to continue.
Let me reshare that. I hope you see it, and I hope the connection from a hotspot is stable. I'm not at full screen yet, but I hope you can see it in full screen.
Yes, we do.
It's not full screen, but we can see it.
All right, good.
No problem to share it like this.
Yeah, all right, good. As I was saying, the discharge process, I hope you heard me until the storing process, is the same as the charging process, but reversed. So cold air gets in, takes up the heat from the material and gets out. Afterwards, we adapt it to anything, steam, thermal oil, or directly at hot air. The storage itself, yeah, okay. Now it's getting... Sometimes we always have to have technical difficulties, right? The storage itself goes to 1300 degrees C. I will show you in a minute while we do this. It is modular. That means the container is the storage itself. Discharging and charging equipment is outside of the storage. And also there are different business units. So if you have one storage that can operate independently, but if you have two, you can cover, for example, 24/7 productions. As well as if you have more, you can cover more power and more load that you can put on or off. It is scalable. We started like 4 megawatt hours up to gigawatt hours, which is probably not really interesting for you, but for the grid it is. It is a very long-lasting storage, meaning we tested the material for 15,000 cycles once a day. That is like 40 years plus, and it is very efficient, 59% for one day. This is electricity to heat. And our material, we took a bit of a different route. We looked first for the material, and we found it in steel slags, which is a waste product. Thus, the material is pretty cheap. We mill it down, add some additional material that improves the heat distribution and heat conductivity, for example, and then we mix it together with an organic binder, for example, to these pellets, but also in different forms like blocks, which are used in certain use cases. And this really has a low carbon footprint as it uses waste products. So this is a nice circular economy. As for the sizes, I mentioned we start low with a capacity from 4 to 12 megawatt hours and a charge from 300 kW to 10 megawatt with a discharge of up to 5 megawatt, which is like a 20-foot container without the equipment. in the medium, we have the PepsiCo project, which I'll tell you in a bit more, where we go into the modularized version. So here you see 2 models. In the end, it will be 5 of this, where we go into higher numbers. And at the end, for really large storage, we do an individual footprint that is not really containerized anymore. So why? And size has something to do with why we use a high temperature approach. When we use, for example, in storage for 300 degrees C process, for example, to make steam for lard, for example, we do it at 800,000 degrees C. Why? We don't need that. But as we discharge the storage, the temperature goes lower. This is with every sensible storage material. So at some point we reach 300 degrees C, and under 300 degrees C you can't use it. So you have a certain amount of energy that isn't used. And this means that when we have high temperature energy storage, we can use more energy from the storage for this process. Thus, the capacity is bigger. This means the storage in itself is smaller, or you need less containers, which translates into lower capex and better ROI. This more useful energy also balances the efficiency of the whole process, because doing charges and discharges, you have some efficiency loss. Why, or what technology comparison you don't have had today is with other technologies such as batteries and hydrogen boilers. Usually batteries also need like a power to heat element or resistance heater like we do, which translate into the same temperature, while hydrogen of course can reach very much higher temperatures. But the efficiency for use as heat is very much better in thermal energy storage, and the costs are very much lower than batteries. Of course, you probably know a lot about hydrogen by now. It's been around since years, and you probably turned your back on it because of the costs. The cost of thermal energy storage really is a fraction of that. The integration effort is also very low. If you have a gas boiler now, you can keep your infrastructure for steam, thermal oil, hot water, whatever, and just replace the boiler. So you have a really easy interface into that. And last but not least, the storage durations. Probably you don't really need a long storage duration. However, when you want to shift energy from cheap times, like Energy Nest showed beautifully, you need a longer storage duration than batteries usually have. So if you want to go from night to day or from the afternoon to the next morning, you need a bit longer, usually like 8 hours, 12 hours. So this really can be done better by thermal energy storage than by batteries. The net zero heat system is what we call the electrified version with a thermal energy storage. So we use renewable electricity, which is also volatile. We make it flexible and thus prevent curtailment, relieve the grid, can use the lower power prices to shift them, and of course, at the end, replace fossil fuels. This can be used in very, very many industries, from food and beverages to chemicals, to even drying bricks or distilling some sort of petrochemicals, even going into steel. We go with commercially available power treatments up to 1,000 degrees Celsius. Here's another look at the economics, showing you different technologies. And you see that for certain steam applications, meaning high temperature steam over 150 degrees Celsius, the combination of electric equipment and thermal energy storage is the best. And this is also because it's heavily dependent on operating costs. Operating costs is what made this project work. This is the factory of PepsiCo in Broekop-Langendijk. 1 million bags of chips are produced here every day for 8 European countries. And almost every emission of this plant lies in the gas boiler, firing a thermal oil network for the frying station, which is frying 24/7. What we do really here is convert wind power, mostly wind power that is used otherwise, to 800 degrees C heat. Our system cares for the whole conversion, the storage, and the heat transfer to thermal oil again, and we use again the existing infrastructure. We replaced a 25 megawatt boiler and this boiler, if avoided, saves 9 million cubic meter of gas and the respective carbon dioxide emissions. And when you see here, the 89% is what big of impact this gas boiler has on this plant emission-wise. And now let's get back to a bit why we do it and why they want to do it. Now, this is the Spanish electricity market, but there's also some examples in the Dutch market, not with this quite low prices. But what we do here have on the day ahead hourly price curve is that we have high price hours and low price hours, sometimes negative price hours. And this is exactly why people shouldn't directly electrify, because you have a higher average than when you just use the small number hours, which looks, for example, like this. So you charge in those hours the storage, and in the other hours you use the storage to discharge, as you by now already heard 2 times. And what this does mean for the Dutch grids, this is a graphic depicting the negative priced hours from 2018 to 2023, and you see the circle gets bigger and bigger. So there's a lot of money in using those negative priced hours. And with that, with the storage, of course, you can relieve the grid. We heard of automatic frequency regulation already. Our storage, for example, has a ramp up of 30 seconds, so you can really go into a bit of details with that. And you can also prevent curtailment. Usually, otherwise curtailed power is very cheap as well. Also, this means that renewable energy projects become more have a better ROI, since they don't lose energy, or they don't need to have such negative prices. So this is both a balancing out for one, the energy generator, as for the energy customer, who has this power then available instead of being it wasted. So there's a need for storage from the utility due to congestion costs, or if you have own renewables, there's a need for storage so that you don't lose money to either giving it to the grid or to just losing it. This is meant by steering of own generation assets. Now I've hushed quite a bit through here, but I researched some applications that might be interesting for your industry, which are hot pressing, pasteurization, any steam needs basically. I don't know exactly if you roast seeds, but if you do, that is a good application. And I'm really, really sure there are more examples we can explore. So for your industry, I most definitely think the net zero heat system is the best choice. We can do waste heat, but as I said, we start from 300 degrees C. So unless you have some pyrolysis process with bio waste, for example, it isn't really any use case for us there. But there are, of course, hot water storages, for example, that take waste heat under 100 degrees C, for example. Or as you heard, energy nest is, I think, starting at 120 degrees C, while we just start at 300 degrees C to make it for our point of view economical. And how are we doing projects? Usually we start when we know what more or less you want to do with an initial concept, analyzing some data, and simulating our storage, how big it is, and giving you a ballpark figure of the investment idea, the capex. Then we go a bit deeper and do a full feasibility study within a month. If you say, all right, we're going to continue with that, we do the detailed engineering, and after that we start with procurement, manufacturing, and construction. Yeah, I hope
Can you sort of round off your presentation? Yeah.
Yes, I hope I didn't lose too much time, but and I hope you forgive me my bad connection.
Okay, thank you very much. Indeed, sometimes technology can hinder or limit.
I promise our engineering is better than our internet.
No problem. Thanks. I'm not sure if there are any questions for Craft Block left, because we are almost at the end of the time frame as well. If not, then thank you all. If you still have questions, you can always ask them afterwards to the presenters as well. Well, for me, it's a short takeaway. A lot of progress has been made in the last few years from ideas to actual realized installations, well, at reasonable sizes as well. I think heat storage is really a decarbonization strategy for heat. What we have seen already is also different heat transfer media used from steam, thermal oil to molten salt and air. And I think also an important item is for a good business case, you need grid balancing and offering ancillary services to the grid as part of the business case. So that's for me. I think everybody, thank you very much for joining. We will share the presentations afterwards. And for the presenters, please stay with us for 10 minutes or so for a short feedback round.
Yeah, thank you. Also on behalf of MVO, thank you, presenters, for having this interesting presentations. I think it's very useful. I will share the presentations with our members and also direct them to you if they have any questions. And for the people having joined us, thank you very much and see you next time.
Okay, I think you can stop the presentation, stop the recording of the presentation.